Bismillahirrahmanirrahim. Assalamu alaikum. Now it's time to convert the dynamical system with repeated eigenvalues. So we have a dynamical system x prime to be a times x, where a has repeated eigenvalues, and we want to convert this into canonical form. We assume that this matrix, this dynamical system is in such a form where a is not in the canonical form. First, I will let you know that the canonical form for the repeated eigenvalues have been seen that it is lambda 0 1 lambda. This one was the form. So given any other system, we can define a t and then t inverse, and then t inverse at will put this matrix into in canonical form, and we will be having this a y to be t inverse a t y y prime to be this, a new system where this matrix will be in the canonical form. So the question is how to do when we have repeated eigenvalues. Before I answer that, I'll one more thing remind you, and that is, if your matrix A is in this form lambda 0 0 lambda, then you can easily solve it. Okay, then you can easily see how the solution would look like. Okay, now consider another system x prime to be ax, where what we know about a is a has repeated eigenvalues. And I'll not be bothering about the theory. I'll not be going into much detail. I'll just letting you know that first you will find out the lambda, then corresponding to lambda you will calculate v, which is the eigenvector, and with the help of these both, then you will solve this system. A times some vector u to be equal to v plus lambda times u, and from this you will find out a u. Once you have this v eigenvector corresponding to this lambda and this u which will come out of this system, and here you will be a little wise and careful, and then you can just define t to be equal to vu, and then you define t inverse, and then t inverse at will be the transformation. So let's do an example. So I'll consider this example. I am given with this system x prime to be equal to a times x, where my a looks like 2 1 minus 1 4. So the system is obviously x prime to be equal to 2x plus y, and my y prime is minus x plus 4 times y. Okay, so now let's see what are its eigenvalues. For finding out the eigenvalues, all we need to do is to calculate the determinant of a minus lambda I to be 0. We need all those lambdas which satisfy this equation. So this is going to be determinant of 2 minus lambda 1 minus 1 4 minus lambda, and all of this set to be 0. 2 minus lambda times 4 minus lambda times plus 1 to be equal to 0. So this is going to be 8, then minus 2 lambda, then minus 4 lambda, then plus lambda square plus 1 equal to 0. Or we can write lambda square minus 6 lambda plus 9 equal to 0. Or you can show that it is lambda minus 3 whole square equal to 0, and that means lambda must be equal to 3. So there are two basically roots, and both are the repeated lambda 1 2 both are 3. Okay, so that means that this system is the system where the eigenvalues are repeated. Now we want to find out the first eigenvector for this. For lambda equal to 3, we will find v first, and for v is eigenvector, so we will just solve this. A minus 3 times I operating onto x to be 0 column vector, and our A was 2 1 minus 1 4, then we have 3 0 0 3, all of this operating onto xy yielding me 0 0, and this gives me minus 1 1 minus 1 and then 1 operating onto xy, and this is 0 0, and this is giving me minus x plus y to be 0, which gives me y equal to x. So if I set x to be t, then y is also t. That means my v vector should be same 1 1. Okay, so far what we have, so far we have lambda equal to 3, which is eigenvalue, and v equal to 1 1, which is eigenvector. And now we need u, and for u we already know that we will work out this equation, AU equal to V plus lambda U. Okay, so I'll set U to be some unknown vector xy. My A is 2 1 minus 1 4, and U is some vector which I am interested in, and V is my 1 1, and this is lambda is 3, so 3x 3y. Okay, and from here I get 2x plus y minus 3x equal to 1, and minus x plus 4y minus 3y equal to 1. And this system yields me, here I have minus x plus y equal to 1, and here also I have minus x plus y equal to 1. So I can, in other words, I can say that this is y equal to 1 plus x. Now if I set x to be 0, then y is going to be 1. So for sure 1 comma 0 can be taken as u. Okay, you can take another u as well, just you will choose some x and then you will be having y, so xy. So my u will be this 1 0. Once I have lambda equal to 3, I have v equal to 1 1, I have u equal to 0 1. Now what I need t, which is the transformation t, and t is nothing but the column vector v and u. Now I need t inverse, and t inverse is what? 1 over determinant of A, which is 1, and then adjoint, which is going to be this, or it is nothing but 1 minus 1 0 1. Now I need what? T inverse A t. So my t inverse is 1 minus 1 0 1, and my A is 2 1 minus 1 4, and then we have 1 1 1 0. So this is same like 1 minus 1 0 1, and now I'll multiply these. So this is going to be 3, and this is going to be 1, and this is going to be again minus 1 plus 4, so this is 3, and then we have this 4. Now we will multiply these, so this is going to be only 3, and this is going to be 1, this is going to be 0, and this is going to be of course 3. So 3 was our lambda, and in fact this is the required canonical form that we needed for the repeated eigenvalue case. So what is the takeaway message? We had x prime to be equal to ax, where our a was 2 1 minus 1 4, and this was not in the canonical form. In other words, x prime was equal to 2x plus y, and y prime was equal to minus x plus 4y. So what we did, we converted it with the help of this t inverse at into another system, which is y prime equal to t inverse aty, and where this t inverse aty is what? It is 3103. Okay, or you can say that y1 prime is equal to 3y1 plus maybe y2. Just I'm defining new variable for these y's. So y2 prime is 3y2. So this transformation defining required me to calculate lambda and then v and then u, and from those we calculate t as vu, and then we calculate t inverse, and then just t inverse a t was all of the thing that was needed. So this if we see the phase portrait, then this is the phase portrait for the original one where lambda is equal to 3, and you can realize that the trajectories are going away from 0 0. In other words, our 0 0 is kind of source, or you can say that it's unstable. But like for the system that we had originally, it's very hard to draw this, but for this in canonical form it is easy to draw this one, as we have previously done with the case in canonical form lambda 1 0 lambda. So both are showing the same behavior. This is also showing that the 0 0 is the equilibrium point, which is unstable equilibrium point, and trajectories are moving away from the origin. It's just because lambda equal to 3 is repeated and it is positive. If it were negative, then the direction would have been inside, but now the direction is outside only because lambda 3 is positive. And this is the behavior for the repeated eigenvalue. This is the behavior repeated eigenvalue and original without converting in the canonical form, and this is the behavior after converting into canonical form. And in the both cases, the natural the basic behavior doesn't change. Like the 0 0 remains the unstable equilibrium, but just there's a there is a there is a changing in how the way trajectories are leaving the origin, or how the trajectories are being repelled by the origin, because it's repeller. When it is unstable, it's repelling away the trajectories. Thank you. In the next videos we are going to move towards the so-called trace determinant analysis. Inshallah, we are going to move to trace determinant analysis in the next videos. Thank you.